Welcome to Mastering Solutions. This question is almost identical to one that we did a couple questions ago, only instead of a lens, which we did previously, this one is a mirror, but the principle is essentially the same. So for part A, I'm going to explain it mathematically and then also conceptually because it really helps to understand both. So if we think about the thin lens equation, we know that the inverse of the focal length in meters is equal to 1 over the image distance plus 1 over the object distance. Now, if you think about what's happening here, we're focusing the sun, right? And so the object distance, or the sun, is way further away than what the focal length of our lens is. And so the object distance, for all intents and purposes here, is approaching infinity. What we say is it's optical infinity, meaning it's so far away that when you convert it into diopters, it essentially doesn't matter. And that's because as this number in the denominator goes up or gets closer and closer to infinity, the overall number goes down. And so this one approaches 0. So for our question here, we can treat this as if it is 0. So when we rewrite our equation now, we have 1 over the focal length is equal to 1 over the image distance. And if we take the reciprocal of both sides, we just found that the focal length is equal to where the image focuses. So mathematically, that's how you see that the best place to focus and get the clearest image is at the focal point. And that makes sense if we draw a picture of it, because we'll say we have our converging mirror here, our concave mirror, and we have parallel light rays coming in from the sun, right? Because they are so far away that by this point, they're essentially parallel. Now, in reality, we're almost never going to get truly parallel light, but for this, it's very, very close. Here's our focal point, and all of these light rays, when they reflect off of the mirror, are going to focus right through that focal point. And so conceptually, this is what's happening. Is the light from the sun, if we place it right at the focal point, that's where we'll get the clearest image, because that's where we get the convergence of all these light rays. So now moving on to part B, the diameter of the image, we're dealing with the image of a circle, right? The sun. And so the height of the image is essentially the diameter, right? They're the same thing. So if we use the equation h prime is equal to h times s prime over s. We've used this a lot in the past from the magnification equation. In this case, we don't care if the image is upright or inverted or whatever. We just want to figure out what the height of it is. So it doesn't matter if we include the negative here. If you keep it in there, that's fine, but we just need the height, which will tell us the diameter. And so we have the h prime is equal to the height of the object, and in this case, it's the diameter of the sun. So this is similar to the previous question that was like this. They're trying to trip you up by writing it this way. Now, maybe it wasn't malicious intent, but it's definitely a spot where students will get messed up, because what they'll do is they'll say, all right, we have 1, 2, 3, 4, 5, 6. So they'll put 1.4 times 10 to the 6 meters into the equation, but that's not it, right? We have kilometers. So really we have to add another 1, 2, 3 zeros. So what we have in actuality is 1.4 times 10 to the, not negative, times 10 to the 9 meters. Now when we multiply that by the image distance, we just figured that out with the focal length, and that is we didn't do the math, sorry. That's the focal length is the 45 centimeters. So 0.45 meters or 45 centimeters. So we have 0.45 meters for the image distance at the focal point. And then the object distance, that's this here, and it's the same thing. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, plus 3 more for kilo. So that's 1.5 times 10 to the 11 meters. So that will give us 1.4 times 10 to the 9, multiplied by 0.45 meters divided by 1.5 times 10 to the 11. So the height of the image in meters is 1, 2, 3. So we'll say 4.2 millimeters. So that is the answer for part B of the diameter of the image, which is the same as the height. So now moving on to part C, we are going to use the intensity formula for this. And it says intensity is equal to power over the area. But we don't want the intensity for C. We want to figure out the power that's captured by the mirror. So if we multiply both sides by the area, we know that the power is equal to the intensity times the area. And so the intensity we're told is 1050 watts per meter squared. And now we're going to multiply that by the area, but the area of what, right? It's the area captured by the mirror, so the area of the mirror. And we're dealing with a spherical mirror, so it's going to be the area of a circle. The area of the circle, as you know, is pi r squared. So we have pi, but what is the radius? We're told that the diameter of the mirror is 24 centimeters. So we're going to take 0.24 meters, divide that by 2, and then square it. So we have 1050 multiplied by pi times the radius, so 0.24 meters divided by 2 squared. So the power captured by the mirror is 47.5 watts. So now let's give us some more space. So now lastly for part D, we need to figure out what the intensity on the image is now. So now we're at the plane of where we're focusing the light. So we already know the intensity formula. We just talked about it. So intensity is power over area. And now we're not talking about the mirror. Now we're talking about the image, like we said. So the power is what we just figured out. So we have 47.5 watts, and that's going to be divided by the area of our image. And so same thing, pi r squared, so pi times the radius, and the radius that we found is going to be half of this value here. So we have 4.2 times 10 to the negative 3 meters. That's the diameter of our image. Divide that by 2 for the radius, and then we'll square that. So we have 47.5 divided by pi times the radius, which we said was 4.2 times 10 to the negative 3, and we'll divide that by 2 and square it. So the intensity at the mirror, or at the paper focusing the light rays is 1, 2, 3. So we'll say 3.4 times 10 to the 6 watts per meter squared. So here are your answers to the question for the intensity, power by the mirror, the diameter, and for the image focal point.